All right. Hello, everyone. I'm Bernd, and today is day 12 of Advent of Code. So today was about hill climbing, and we give him a grid, and each letter in this grid stands for one height. So A is the lowest height, and then B and so on till Z is the highest one. And we wanna go from I've also given him a start and the end, and we wanna go from the start to the end. And in each step, we're only allowed to go to the neighboring positions, and we're only allowed to go up at most one. So we can go from A to B and from B to C and so on. And we're allowed to go down any amount. And then we just want to know how long it will take us to get from start to the end for part one. So how can we do this? Of course, we need to read the file input and split it into lines. And then we want to parse this grid. So our grid will be a dictionary, which maps from a position, which is a tuple of two integer, to a height. And we'll also keep track of this, or look at the start position and the end position, find the start and end positions. So we iterate for all the lines on each line. And then we look at the letter. If the letter is an S, that's the start. We set the grid height to 0 and mark it as a corresponding start position. Similar if the letter is the end position. And otherwise, we rely on the order function, which gives us the Unicode code of a letter. And we compare this, and conveniently, all the Unicodes of the letters are in order. So we can compare this code to the code of the letter A, and this will give us the height. Okay, then in order to solve the problem, we will start at the start, and then at each step we will consider the set of current position we can reach. So after one step we could reach this A and this A. After another step we could reach this B. From this one A, for example, we could reach this B, and we can also reach this B, but we could also step back to S. So that would be the set of positions we can reach after two steps and so on. So in order to achieve that, we have this do one step function, which takes the input of the grid and the set of current position. And then we go for each position in these current positions. We consider all the neighbors. And then we check if the neighbor is in the grid. And if the grid, if the height at the new position is as most, the height at the old position plus 1. If both of these are the case, the new position is a valid, we can step to the new position. So we add it to the set of new positions. And then we return that. And with this, we can solve the problem. So we first pass the lines. We start with the current position, which is set, which just contains the starting position. We keep track of the number of steps, and then we do something while the end position is not in the current position. So as soon as the end position is reachable in the current positions, we know we're done. And while this is not the case, we update the current positions by doing one step. Yeah, this is already a solution now. We can test it on the test input, and that looks very good. So we can also do it on the full input, and turns out this gives us the right result. Part 2 is slightly different. So in this case, we want to consider all the starting positions which have letter A, so are the lowest height. I want to find from all of those the quickest path that goes to E. So this would be a bit inconvenient. I guess we would have to do a lot of iterations, but instead we can turn the problem around. We can think of us just starting at E and at the end, and then going down one step at a time until we reach a position which is of the lowest height. So for this, we can change the do one step function slightly. Now we're going to go down instead of up. So essentially we used to have this line. So the new position can be at most the old position plus 1. Now the old position should be at most the new position plus 1. So that's the position, like the indices here change. And with this, like we now kind of simulated going down. So in order to solve, we start with the current position, which is set, and this time contains only the end position. And then in each step, we will figure out the current position, which is what we can reach from the end position in that number of steps. And then we will consider the current heights, which is just all the heights of the positions that in current positions. And if 0 is in the current heights, that means we reached 1A. And that means there is a path from A to the end in that many steps. So we return that number of steps. Otherwise, we just continue and get again the current positions. Okay. You can also run a little test on that with a bit of luck. Yeah, that looks good. So that's already it for today, part 12, day 12. I hope you enjoyed today's puzzle. Best of luck for the future, and see you around.